Hi class. So this video is to provide you with additional information in relation to the Mechanical Engineering 215-211 project number 1. Okay, so after we finished the midterm presentation and when you all went through your PowerPoints or the slides for all these categories, um, it became evident that some more explanation needs to be made to clarify some misconceptions and some misunderstandings. Okay, so um, for all these categories, there will be some additional information in this video to help you towards your final exam and the final report. All right, so let's take the case of CAD design. So what was needed here? We were looking for primarily dimensions and locations. Okay, dimensions and locations of what? First of all, dimensions and locations of all insulation materials. Okay, so you're allowed to use as many materials you want to use as long as the external dimensional constraints are met. So for example, in this case, I'm showing 3 insulation materials here. Okay, and it could be more, it could be less. So there's this yellow, there is this light brown, and then there is kind of a maroon. So these 3 colors, what we are looking for is what is the distribution of thickness on the sides and what is the distribution of thickness on the bottom. Okay, and if you have some in between materials, where exactly are they located? Okay, so all these dimensions needs to be shown if that's what your design is. Then you need to show the dimensions and locations of the metal barrier. Okay, so if you're choosing to put so if you look at the constraints, the barrier basically is a physical barrier such that your cup doesn't directly touch the thermistor and the cup doesn't directly touch the heater. Okay, so as long as you cover those 2 things, um, the barrier is good. You don't have to have the barrier everywhere. It just needs to cover the heater and the thermistor. Okay, so if you have a really high thermal conductivity barrier, for example like an aluminum foil, and if you take it all the way up to the top, you can have heat losses. So maybe you want to stop them from going all the way up. Okay, so things like that. So how do you want to give those dimensions? Okay, so that's another example of dimensions. And the locations for thermistors and heaters. So in this case, I am probably going to place the thermistors and heaters in this yellow insulated area, and the yellow insulation probably could be a flexible insulation, and I'll get into more details in the coming few slides. Okay, so the location of thermistors and heaters and the holes through which all those wires to connect to the thermistor and heaters, the location of those, things like that. All right, so when you also design your CAD, you should remember that this is not a fully cylindrical cup. There is a small taper. Okay, it's not exactly straight, so your design have to account for that. And also remember that the bottom is not fully flat. So that's what the purpose of the CAD design was. First, understanding the size of the cup and making sure you know what is the inside dimensions needed in the holder to place all these different materials, the insulation, the barrier, um, having the pass-throughs, space for heaters and other wires, etc. So that was the purpose of CAD design. Now, what did we mean by thermistor placement, heater and thermistor placement? The goal was heater should provide most of the heat to the water and the less of the heat should be lost to the surroundings. Okay, so that would be a better, more optimal thermal design that optimizes the heat going to the water instead of losing it to the outside. So this means the heater should be in good thermal contact with the metal barrier, and the metal barrier should be in good thermal contact with the cup, and then the metal barrier also shouldn't lose a lot of heat directly to the air. So, stop it before it reaches the top, for example. Um, So thermistor must be in good contact with the um, metal barrier and also with good contact with the cup for reading accurate temperatures, right? Um, and a good way to contact would be the vertical location because the cup is curved, and if you put it horizontal, maybe the contact is not that great, right? So you may be better advised to put it vertical, or you could put it on the very bottom of the cup where it's flatter. So it's up to you, but ensure good contact. Um, Another aspect of placing the heater and thermistor is to ensure that it's always pressed up tight against the cup warmer. Um, so one way to do that would be having some kind of elastic uh, material or some kind of spring that will compress when the cup is in place and push up against the surface. You could achieve this by several methods. One of the methods is shown here. So the yellow portion here is basically a flexible foam insulation. Okay, so flexible insulation, and it is enclosed in rigid insulation materials, one or two. But if you have a flexible insulation material and you arrange your wires and the barrier to stick out a little bit when there's no cup, right? And when you place the cup, that gets pushed in, right? So that basically makes it a tight contact. So this is like a flexible, like a sponge that can be pushed back in and it compresses when the cup is in place. So if you have an insulation like that, that'll help with, um, you know, better thermal contact for both the heater and the thermistor. And you can, for a certain extent, be confident of your temperature measurement and confident of the heat transfer efficiency. And good examples are foam insulations, like open or cold foam, closed cell foams are good examples that will do that. You could also use some glass wool that can also get compressed. Another thing to notice here is when you place heater and thermistor, you have to try to make sure there is some gap between them. You're trying to measure the water temperature, not the temperature from the heater, right? So this thermistor should try to respond mostly to the water temperature. So each time the heater turns on or off, you want to minimize the direct heating of the thermistor by the heater, okay? So that as much as you can minimize that, you will have better response to the water temperature. And one way to do that is to make sure there is some physical separation, more physical distance between those two. They don't touch each other. The other way to do that is if they are all connected by a high thermal conductivity aluminum foil or copper foil or whatever, right, a metal foil, you create a break, a discontinuity in that foil between the heater and the thermistor. Okay, so if the thermistor is at the bottom, for example, you may have to have a thermal break like this. If it's at the top, it's like this. Essentially, it looks like this, right? And where this blue color is the barrier material, and you have cut the barrier material to it doesn't have to be a big wide cut, maybe a small narrow cut that stops direct conduction through the aluminum. Okay, so the heat that directly heats up the thermistor is slowed down. At the same time, the thermistor is separated from the cup through a barrier material. Okay, so you could do something like that to have your thermistor isolated from the heater to a certain extent. Now, the third aspect was the insulation material selection. A lot of you focused on cost and all that, but that was not part of the problem. It was never a question. It was not asked in the problem statement, right? The goal is to satisfy the problem statement and follow the constraints. So the properties that matter are thermal conductivity. Okay, so the insulation material, the primary property that matters is the thermal conductivity. The second one is how easy is it to manufacture for the purpose of this project. Okay, there might be materials that are really good. You could have a vacuum sealed cup, but it's difficult to manufacture for the project, right? So it should be practical for the time frame of the project, easily manufacturable to correct dimensions, right? You want good contact with the cup. So those two are the main. And the third one is the ability to withstand operating temperatures. Okay, it shouldn't melt or catch on fire or something like that, but the chances of that is very little because most materials should be able to take the temperatures that we are going to see here. I don't expect it to go about 90 degrees C if you have everything controlled well. Only if you design really at the extreme, there is a chance that the thermistor doesn't see the heater, the water temperature, and the heater gets extremely hot. And you have insulated so well that it goes to up to 85, 90. But I think the temperatures should be lower than that. Okay. So a lot of materials that you would end up finding for this project would have an operating temperature above 95 degrees C or close to 95. So most likely you should be okay. But if you're not okay, if your material, for example, this gray material, if its operating temperature is 80 degrees C, for example, then all you have to do is make sure that the yellow material, which actually contacts the heater, that has a higher operating temperature. So you could use two materials, one that is flexible and can meet higher temperature requirements and help with good contact in a small location, and then that material isolates the more rigid material, which may not have a higher operating temperature. So you could do things like that. Okay. Um, so operating temperature, let's say if for this gray material is 70 degrees C, and if you use a flexible material like glass wool here, which has very high operating temperature, then it should be safe to operate these two together, even if the temperature here gets close to 90 or 100, okay, because it will be protected by the yellow material. So those are the only three things that you have to consider: the thermal conductivity, which will ensure that most of the heat goes to the water and not to the surroundings, and how easy to manufacture, and make sure that it will operate okay in this somewhere in this range of temperatures. So that's about insulation material selection, and here you can see some examples that I had in mind. For example, for the rigid material, I was thinking something similar to EPS and XPS, very commonly used in the industry for small projects and small fixes inside big appliances. So these are perfectly okay, and they might have a max operating temperature close to 100 or slightly lower than 100. So they are kind of borderline. So you could use a glass wool type material here next to the heater for flexibility and prevent damage to this. And these things are easily machinable. And you have several different flexible materials, not just the glass wool. You could have foam type flexible materials, and the foam comes in two different forms. You can have foam that has closed cell pores, or you could have open cell. So closed cell foam pores, they are more rigid. They won't. It is more difficult to compress them, but you should be able to find some that are flexible enough for your project. And open cell ones are very easily compressible, but the open cell ones have a higher conductivity as opposed to the closed cell ones, which have more better insulation properties. Okay. All right, so that's about the dimensions, CAD, material selection, and the heater and thermistor placement. Now, one thing that almost everybody missed is how to determine your cut-in and cut-out temperatures for control. Everybody received two thermistors in this project. Okay, so the purpose of those two thermistors that was explained before was to help you determine the cut-in and cut-off temperatures that you want to operate your thermistor such that the temperature of the water is between 54 and 56, right? So you want this thermistor, for example, thermistor 2, denoted by this purple line, controlled between 54 and 56, while your thermistor is controlled between some other temperature range. That other temperature range is called the cut-in and cut-out temperatures. And the reason for cut-in and cut-out temperatures is that's when the heater cuts in or the heater turns on and when the heater turns off. So heater turn on and off is controlled by this thermistor and by the limits T low and T high. How do you find T low and T high? And first of all, why are these two temperatures different? So think about it. So you have two temperatures. When the heater heats, um, the heat goes to the water and heat goes to the thermistor in two different paths. First, the water has to heat up. It has higher specific heat than anything that is between the heater and the thermistor. Okay, so the water might take longer to heat up. So the thermistor might respond faster. Okay, so the moment it starts heating, the water might take longer to heat up. It's slower to get to the same point. It will lag behind the heating of the thermistor 1. And the temperatures will also be different. Okay, so by the time this temperature reaches a very high value, the water would have slowly warmed up to 56. And and when it cuts off, this might still keep warming because there's a delay. There's a thermal inertia. Okay, but all that we want to know is what is the high and low to which this thermistor needs to be controlled, such that this water temperature at the center is between 54 and 56. This is a classic problem in all the appliances that use temperature control. Any appliance that has a temperature control, its sensor is located somewhere else inside the appliance, and you want to control the temperature of something else that is located far from the operating mechanisms of the appliance. So usually they'll have to find this cut-in and cut-out temperature, which is a little bit offset from the actual cut-in and cut-out temperature of the target material, which is 54 and 56C. Okay. Now, how do we determine that? So, first of all, you will have to make a setup which has two thermistors, and you should be able to log the data from two thermistors, and also notice what the heater is doing. Okay. So let's look at all the steps that is needed to find this. So you first of all need to collect data from both thermistors, one from the center of the water and one from the where you plan to finally put the thermistor on the cup warmer. And you have to collect the data for both the heater on and heater off conditions. So first thing to do is write a code to force the heater to be on and off periodically. Okay, forget about temperature based control. Just write a code to turn on the heater and turn off the heater for 10 minutes and 15 minutes. It's up to you. So turn it on and off cyclically, okay, periodically. So a good example is turn it on for 10 minutes and turn it off for 15 minutes, and then turn it back again for 10 minutes, turn it on for 15 minutes. And you place hot water into that hot water cup into that system and let it cool down and force and notice what the heater is doing and make sure it logs several cycles, 10 15 10 15, several cycles, keep logging. And when you have data like this, you copy that data to Excel and plot the graph like this, right? So you need data of time, data on the heater status, whether the heater is on or off, the thermistor 1 temperature and the thermistor 2 temperature. Okay, so if you have that, you can create a plot like this. Okay, now copying this data to Excel is itself tricky, and I was hoping that somebody would present that in the midterm. Anyways, you could try to copy directly from the serial monitor of Arduino, copy paste to Excel. And if you have problems there, I have given you another example on how to do that here in this video. Okay, so anyway, you have T on, T off, T on, T off, and you got multiple cycles and you got stable cycles. And once you have that, copy that data in Excel, and from the Excel now you find T1 low and T1 high. Okay, so you want to know from the data what is the lower values of the cycles for thermistor 1, which is called T1 low. Thermistor 1 is the green one, right? And thermistor 1 basically means the thermistor on your beverage warmer. Thermistor 2 is the thermistor of the water, or thermistor located in the water. Okay, so find the min and max on these cycles, on these stable cycles for green thermistor, which is thermistor 1, and also the T2 low and T2 high for the purple. Okay, so once you have those two things from the Excel, now the goal is at what T1 high and T1 low value would you get a T2 low of 54 and T2 high as 56. So what I mean by that is you've got a T1 low and a T1 high, but your T2 low and T2 high could be something like 60 and 62. Okay, but what you want is 54 and 56. So your goal is, how can I change this such that both of them moves down and the blue and the red lines exactly represent 54 and 56, so it's controlled between those two temperatures, right? And it's a trial and error method, but this is the easiest way to get there, and you can find your own methods too. This is just one approach. Okay, there are several different ways to do this. One way to do that is find a relationship between these two, assume that it's linear. Okay, so the limits on one thermistor, let's call those as T1. Okay, the limits of thermistor 1, the lower and upper limits of thermistor 1 are represented by T1, and the lower and upper limits of thermistor 2 are represented by T2, and assume that T1 is a function of T2, right? If that's the case, we know what is the T2 that we are looking for. We are looking for T2 between 54 and 56. What we assume is, we assume that the function is linear. T1 is a linear function of T2, okay? Which is not true, because that's why this is a trial and error function, trial and error method. So if it is linear, you can write an equation for slope and intercept using the four temperature limits that you got looking at the graph, right? And once you know M and C, now you find the T2 low, the T1 high guess and the T low guess by using 54 and 56 in the equation. So now you have an initial guess value for your T1 high and T1 low, okay? And those numbers are T high guess and T low guess, because I'm calling it guess because it's still not accurate, okay? It's an initial guess value. Now use this and you write another code, which will be similar to your final code, to control heater on off based on thermistor 1. Now your heater should turn on or off based on thermistor 1, and its temperature should be controlled between the two guess values that we just determined, the low gas and the high gas, and you control the T1, the green thermistor, between those two. And collect the data and copy the data, plot it, check whether the T2 high and T2 low are 54 and 56. If they are not 54 and 56, if they are slightly off, adjust this or this value depending on whether it's off on the top or off on the bottom, okay? Adjust it a little bit, try it again, adjust it a little bit, and you might have to do it 2-3 times to get it more accurately. And you don't have to exactly control it to 54 and 56. It could be inside 54 and 56. So for example, you can control it to 54.2 to 55.8, because that will be inside, right? So adjust such that it's always inside. That's all is required, that the temperature of the center of the water does not go outside, okay? So um, that is basically how to find the cut-in and cut-out temperature. So using guesses and iterative approach, trial and error to get the value. You could use other methods too. Another thing I wanted to touch base on was the LED status indication. It seems to me that a lot of the groups are understanding this differently from what was asked in the question. Green LED is only to show whether your temperatures are in control or not. Okay, so when the temperature is on, sorry, when the green LED is on, that means the temperature is between 54 and 56. Okay, that's it. And it's off outside. So anytime it's outside, it's off. So you can follow this red dashed line here. Okay, the moment the green LEDs, the green line gets inside 54 and 56, this green dash line goes on. Okay, and it's always on after that because it's always inside, right? On the other hand, the red LED is to show when the heater is on and when the heater is off. So it should turn on each time the heater turns on and turn off each time the heater turns off. Okay, so ideally, if you have everything working correctly, uh, once the green LED turns on, it will stay on, and your control will completely control it, right? It should remain green for the rest of the test, if it's controlling well. And the red LED should periodically turn on and off. Okay, so on when the heater is on and off when the heater is off. And when does the heater turn on and off? Whenever it needs to control temperatures, right? So if you have designed the heater to turn on before it hits 54, for example, if you're controlling at 54.2, the LED should turn on exactly at that same time, right? And if you're turning off the heater before 56, way before 56, for example, then it should happen the same way. And by the way, these are not 54 and 56. This would be your T low and T high. Okay, um, this is basically what is represented here is the center temperature, but you get the idea what I'm saying. So in this case, we are just talking about the center temperature here. Okay, all right. Now, um, earlier in the step 2 here, or step 3, we had talked about copying data to Excel. So the direct method is, of course, open the serial monitor and copy and paste in Excel. Now, when you copy and paste in Excel, if it is not separated by delimiters, like you can see I've separated everything here by a comma, right? If you use a delimiter like that, when you copy paste, it's easier to put them into different columns, okay? So in your code, try to output all the text and the numbers separated by commas when you're outputting into the serial monitor, okay? Um, and you can use Excel formulas or Excel data input methods, different methods to separate the comma separated values and put them into different columns. This thing should work, and I haven't tried it for large amounts of data, but if you have a lot of data and you want to copy paste, this might miss a lot of data. I've heard about problems where people can only copy what's on the monitor at that time. Okay, it misses a lot of data from the past. If you're facing that kind of issues, you might need to use a terminal program that copies data from the serial monitor and creates a new file. There are third-party softwares like PuTTY, Teraterm, and CoolTerm that people use widely to do this. Okay, and it's very easy. You can watch several YouTube videos, search for YouTube videos for transferring Arduino data, serial monitor data with PuTTY or Teraterm or CoolTerm, and you'll find plenty of videos. You can also use some AI, free AI sources to learn more about these three things. But I've given an example of PuTTY that I've used before on how to log Arduino data using the PuTTY program. Okay, and other ones you can search internet and find those, and you can pick your software. All of them should work. Okay, so you have to basically communicate through the serial port and log data. Get the baud rate right. It's usually 9600. Okay, and go through these instructions, and you should be able to save the file. And use that file, open that file using Excel and save an Excel file and create the charts like this to figure out your min and max values. Okay. All right. So now let's look at the control logic for heater on off based on time. So this is in relation, or this relates to the determination of cut-in and cut-off temperatures in step 1 um, of the slide that was shown before. For example, here. So it mentions write a code to turn off the heater periodically between two different time periods. They could be same time period, so it's on for a certain time and off for a certain time. So two variables on and off, they control the heater on off times, and that is repeated cyclically. Okay, so this is an example code, and you can search for the full code yourself online. Use some available open source or free AI code generators, um, and make sure you debug your code. Okay, so in this particular case, we are doing this using a heater status boolean, which changes its values based on time. So if the time is elapsed for T on, then the heater status will change from on to off, and if the off time has elapsed for a time period of T off, it will change from the heater status will change from off to on. So as the heater status changes, we'll turn on the heater from on to off or off to on. So we'll change the heater on off based on the heater status boolean. Now, what are the variables that are of significance here? So there are two time variables. One is the last heater change time. It looks for the timestamp, exact time at which the change of heater happened the last time. So if it was an off and it happened at 2 p.m., then 2 p.m. is the value that's stored here, right? And if it's on later on at 2:10 p.m., then this value gets updated to the next value. Okay, so it keeps track of the time change, and the current time function, this variable looks at the actual current time in milliseconds. Okay, so those are the two things that are needed, or three things that are needed to step through this logic. So if the heater is currently on, the first if logic happens when if the heater is currently on. So if the heater status is on, then you'll go inside this loop, right? And you check for how much is the elapsed time. And if the elapsed time, current time minus the last change in heater, is greater than the on time, because this is already on, right? If that elapsed time has passed, now you have to turn it off. So you turn off the heater. So it'll keep leaving the heater on until it's off. And then when it's off, you will get out of this loop because the status has changed, because you change the status to false. Okay, and when the status changes, you change the relay, turn off the relay. You can also monitor the red LED, and then you'll set the value of the last heater change time. Okay, if that is not the case, else if the heater is already off, if the heater status is already off, if you'll do the opposite thing. You'll check for the off time, okay, and do everything the same way. This time you will turn the heater back on, okay, and then you'll keep looping. So this is a simple way to do this. You can do it other methods, but this is a good example of this code. Now let's look at the other code, which is controlling the heater on off and the LED on off based on thermistor. This is in relation to step number 9. Okay, so write a code to control heater on and off based on thermistor 1. Okay, so here you're controlling between a high and a low value, thermistor 1. Okay, so I would say step 9. So this, if you try to use some code generators or open AIs online, most likely you'll get the wrong code. Okay, this is the code that will most of the generators will generate first, but this is wrong. So you have to understand why it's wrong. You can see that if it's looking for a temperature T low, so if it's less than that T low, it's asking to turn on the heater or turn on the relay. Okay, that's all correct. And if the temperature is above T high, turn off the relay. That makes sense. And if the temperature is in between, the relay is off. That is not correct because when you're heating, the temperature is in between and the relay needs to stay on. Because of this else statement, what will happen is the moment you're above T low, it will turn off and then it'll turn on again, turn off, turn on. So basically, you'll be controlling exactly at T low value and a lot of very fast on and off. The moment it goes above, it turns off. Okay, um, so that is wrong. So how do you fix that? You have to keep asking the AI code generator, or if you're doing the coding yourself, you have to think about how to ensure that the heater stays on for the whole duration between high and low. Okay, the one way to do that is again using a heater status boolean. And this boolean, if it is less than T low, it will be a status of on, and if it's above T high, it's status of off. So the boolean will only change values at the extremes. Okay, so if changed value to on, the heater will stay on, stay on, stay on, stay on, and it will change value only if it hits here. And then it will be off, 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 continuously comes down, and then it'll change value when it hits here. Okay, so the boolean will only change value at the low and high, but you have to initialize it. Initially you will say that it's false. Okay, and then when it first recognizes that it's below T low, that's when the heater will turn on. So let's look at the uh, algorithm here. So it has a first check for temperature. So if the temperature is less than T low, uh, then so this particular loop is only for the heater status. Okay, so it's checking the temperature less than T low, then the heater status should be true, and if the temperature is greater than T high, the heater status is false. It doesn't tell you anything about what should happen in between. It's only changing here and here. It doesn't say about in between temperatures. So there is no change that happens between T low and T high. Okay, it can only change when it reaches here or here. Now controlling the heater based on heater status. So you've set the status here, and now if heater status, this means if the heater status is on, okay, if the heater status is on, that means you should basically turn on the heater. Heater status is on because the temperature is less than T low. So if it is less than T low, you have to turn on the heater, okay? And right, the LED, red LED should stay on when the heater is on, okay? Else, if the heater status is off, the heater should be off and the LED should be off, okay? So this will only happen here and here. So if it's turned on here, it'll keep going until it's turned off here, and it'll keep going until it's turned on back again here, okay? So it doesn't say anything about in between. Now, in between, what should happen? If temperature greater than or equal to T low and temperature less than or equal to T high, then you should worry about your green LED. Okay, this is when the green LED should be high. It should be high in between these two. Okay, temperature is within range. Else, the green LED should be low. So if the temperature is outside, the green LED should be low. So this is a very simple control algorithm for making sure the heater turns on and the red LED turns on exactly when it should be, and the green LED turns on exactly when it should be. Okay, all right. Now let's look at circuit design and portability. During the presentation, uh, everybody had their own diagrams for circuit design, but what we were looking for is an actual circuit diagram. Okay, what does that mean? We need to know how we are connecting different things to different pins on the Arduino. Arduino has a lot of digital input output pins. Okay, there are several input and output pins on Arduino. which pins are you planning to connect which component? That was something that was missing, and you should include that in your final report and your final presentation, okay? Um, how are you planning to connect those to the LEDs? How are you planning to connect those to relay? How are you planning to connect those to resistors, power supply, heaters, quick connectors, etc.? So this is a sample circuit diagram. It's not for our project, but you see every component is shown here and it's going to different locations on the Arduino. It's showing where you're connecting to your actual actuators and fans and things like that. Where is the resistor? What is the value of every resistor? So that's what a circuit diagram is. Looking at a circuit diagram, somebody should be able to copy your circuit. Okay, that is the purpose of a circuit diagram. If you give me your circuit diagram or give your friend your circuit diagram, he should be able to replicate without further explanation. Okay, everything should be explained in the diagram, how things are connected, what is the power supply voltage, what is the value of every component. That was missing. So please include that in your final presentation and reports. For portability, what we wanted was um, how you can neatly arrange all these components inside a control box. And by components, I mean the Arduino, the power supply, the relay, all that, such that they are neatly arranged. And when you move it for test and everything, it shouldn't be that there's a loose connection and it's not working, there's a short circuit, things like that shouldn't happen. Okay, so what is your plan to secure? What is the plan to connect? Are you soldering the joints? Um, what kind of connectors are you using? Those are the things that we are looking for. Okay, and where are your locations for A, B, C, and D connectors? How easy it is to access them for measurements before the test, things like that. That's what was we were looking for in terms of design and portability. Okay, so basically make sure your connections are secure and there's no chance of loosening, and you're also following the requirements for the cable lengths. All right, so hopefully this gives you enough information to prepare for your final exam. All right, thank you.